Hello everyone. Today, as you can see, we're going to continue with our likelihood and efficiency journey. So what we're going to do is, as I mentioned in the previous video on the channel, we're going to, and as a matter of fact, I'm still using the same, let's say, file. We're going to pretty much talk about a very straightforward corollary to this one, where I remind you, we said that under suitable regularity assumption, there exists what? An unbiased and efficient estimator Tn of our parameter theta, such as if and only if. So we were characterizing this existence, if and only if that you could have written the curve function as a basically it was related to the information, official information. So there was some sort of a linear. It was equal up to a constant. Now, we proved it, and the proof was pretty interesting from both a probabilistic and approach. Then was also some mathematical analysis, reanalysis involved. Now, what we're going to do is we're going to basically state a pretty important result, which is this. I'm going to call it corollary. And then we're going to provide an example. So finally, something to get an idea of how to use these results. So this corollary basically states that once again, under suitable assumption, forgive my poor writings, under suitable assumption, let Tn be an unbiased and efficient, hence you can reach the limit, the Rauckramer limit, and efficient estimator of theta, and let theta and hat be the MLE of theta, satisfying, that's right here, satisfying curve function equal to 0. So it's the solution of curve function equal to 0, which I remind you, this is nothing but the derivative of the log likelihood. Hence, this is the MLE, maximum likelihood estimator of theta, right? Perfect. Okay. The claim is they're equal. So the proof is extremely simple, as once again it follows from the previous theorem. Once again, I remind you, we claimed that from an unbiased and efficient estimator Tn of theta, then this curve function could have been written such as Tn minus theta, so Tn, the estimator minus the parameter times the information matrix. So we can write this curve function as Tn minus the parameter times official information, right? And if we put this equal to 0, then we have Tn minus theta equal, times information is equal to 0. This is nothing but Tn, if I find the solution of this equation, which is a solution of obviously the square function equal to 0, then we find that Tn, let's write it for an extent, is equal to theta times information, official information, obviously. So this is theta as a solution. We're solving for theta. We get that the theta that solves this is also the theta that solves the square function to 0 by this equality. Hence the claim. So obviously pretty straightforward. So let's look at an example. So here what we're considering is we take our random sample from a from a Poisson distribution. So I like to write this way: Poisson of obviously you know this is the distribution that generated the process. Will be this is the way you should formulate it. Obviously with theta non-negative, that's the first one, and we consider the sample mean. And I've been taught to write it this way, the sample variance. Now this is the, as you can see, is the unbiased estimator for the sample variance because of this 1 over n minus 1. This is the unbiased estimator. So these are unbiased estimators of this unbiased estimator of the mean and this unbiased estimator of the sample mean. Now, the interesting property of, so once again, as I said last time, I like to call it memo, whether that is right or wrong. So let's recall that for a Poisson distribution, the mean and variance are equal to the parameter, right? So at this point, you may wonder, which one is the best estimator of the parameter? And that's what we will try to solve. So to answer that question, what we can do is we can look at, so we know, I think there's no need to prove, they're both unbiased. So, and are unbiased estimators of our parameters. So let's check for their variance. So the variance of the sample mean, what is this equal to? So this is equal to theta over n, and you can actually prove, and I'm going to skip the details because that's just part of the example. You can prove that the variance of our sample variance is equal to this thing right here, which is obviously the same plus something larger than 1. Hence, is a more efficient estimator of theta. More efficient doesn't mean it is efficient, right? It is better in terms of efficiency. It has a lower variance than the sample variance. So we prefer this. What it means basically, it is we are obviously when we're talking about statistics, what we're doing is we're trying to extract as much information from the data as possible. So obviously when we do statistics, we are kind of diminishing the dimension of the data, right? So we are trying to get a summary of the data, but however, we do not want to lose information. And so that's why we need to ask ourselves, okay, we're using these new objects called estimators. Which one is the best one? Now, obviously, what we can do is we look, they're both unbiased, which is a very nice property. We'll look for an estimator. And we also can see that when we confront, we look at their variances. This one has a lower variance, which doesn't mean it is efficient. it is more efficient than the other, but it doesn't mean it is efficient. Now, so in a way, we are taking less risk when we decide to use the sample mean than when we're using the sample variance as an estimator for our parameter. Awesome. Now let's proceed with the example. So once again, we're looking at the fact remember, we started with the claim that the MLE estimator of our parameter under these assumptions is equal to the efficient and unbiased estimator. Now, if we consider the log likelihood, and this is equal, I remind you, this is equal to the log of the likelihood, and this is equal to log of, sometimes I write log, sometimes I write ln, it's the same thing. I mean, in high school, your chart is different, but throughout my math career, every time I've seen written log or ln, they both meant the same thing. Nobody uses the log base 10. I mean, people use it, but it's not as common. That's just something interesting. So, this product of the PDFs, right? So this comes down to be the sum of the log, right? Perfect. So blah blah blah, for a Poisson, this comes down to be theta, the sum of xi, minus the sum of the log. Right, so the square function, which once again it is the derivative of a log likelihood, is equal to respect of theta. It's going to be minus n 1 over theta. Right, this does not have theta, so it's equal to 0 once you take the derivative. Perfect. So the Fisher information is going to be equal to minus, so you can write this as, that's why we need if you remember the theorem, it's under certain regularity assumptions. The derivative of the square function, which will be equal, this guy right here is equal to minus. Many times you see it formulated this way in textbooks. Same thing. Perfect. So this is equal, once again, we take the derivative of that thing, and it is n over theta. Where this, where does this come from? Well, if you take the derivative of this guy right here, which is curve function, to respect of theta, you get just this, so minus 1 over theta squared. This is a constant. Then you take the expectation. Obviously, the expectation of, with the minus in front, so let's already get rid of that minus, right? Expectation is linear. Expectation of this thing. However, remember, if you put a 1 over n, you have your sample, this would be the sample mean. So if you do that, you gotta do this, right? So the expectation, what is the expectation of the sample mean? It's theta. Theta squared, theta, and over theta. There you go. Perfect. And okay, so now we can write that this curve function is equal, which is equal to minus n plus. We're basically 1 over theta, right? If we bring it here, is equal to what? To Tn. What is Tn? Tn minus theta times information. Now, Tn is our sample mean minus theta times the information, right? Because you can prove this is actually, if you remember, this is the information, Fisher information, and over theta, what was the variance of the sample mean? See, it's 1 over, remember, if the Rao-Kramer. So an estimator is efficient if its variance is equal to 1 over Fisher information, right? So it is. So it is efficient, which once again, up to this point, we didn't prove it was efficient. We only proved that this was more efficient than, so it had a lower variance than the sample variance. However, we did not say it was efficient. Now, once we have the efficient information, you can see that it actually is efficient. So here's our unbiased and efficient estimator of theta minus the parameter times the information matrix. So this, if we solve for theta, we get the MLE. And so simply, you can see it's equal to 0. So at this point, you can, we can think about it both ways, right? We've actually seen, because we knew about, so here, because previously we calculated the variance, but if we didn't have the variance, so if we didn't have this, then what we calculated is here, if you put this, God, I'm so disorganized. If you put this equal to 0, you get your, and you solve for theta, you get your MLE estimator, maximum likelihood. So if you solve for theta, you get that the theta is equal to the sample mean. So, it works both ways. You can say that you found this to be the MLE, and you found this to be also the efficient estimator. And because this won't be equal to 0 unless n is 0, but n is always larger than 0. It is at least 1 as a matter of fact. And so the only way this is 0 is if theta is equal to this thing. And now I'm writing really bad because I'm in a rush. Okay, so that's the only way this is equal to 0. And there you go, both way. This MLE is equal to the efficient estimator. The efficient estimator is equal to the MLE. And thank you for watching. Any questions? Sorry for the confusion at the end. Yeah, any question, you guys let me know. And once again, if you want to see the proof of the previous theorem about likelihood and efficiency, you find it on the channel. Thank you, and I'll see you in the next one.